Okay, class, let's get started on question 11. This is about investing and exponential growth, and so or continuous and compounded continuously. So some key words here that tells us that we're going to be using one of two formulas. So we're either going to be using our compound interest formula, where we have A is our future amount, P is your present or the amount that you invested or spent. 1 plus N is the, this should be rate. Hold on. Let me do a quick erase. I was going way too quick. And so here we would get R over N times T, where R is your rate as a decimal turn to a decimal. And then time is in years. Or the other formula that we could be using is A equals PERT. E is a value that's continuous, never stops. It's almost like pi, principal rate times time. So let's take a look really quick and talk about how to set this one up. Compounded annually. Compounded annually means it happens once a year. So then we would have, we're looking for our future amount, find the amount in the bank after 9 years. If you invest $6,000, that's coming from the beginning problem, 1 plus a rate of 10%, so that'd be 0.10, all over N, the number of times it compounds in a year. In this case, it would be 1. 1 times how many years? 9. And so essentially, as we go through this compounded quarterly, this value right here would change to 4. Our N is how frequently it will happen in a year. And then compounded monthly, that 1 will then turn into 12. And so really what we're going to do here is just go over to Desmos and do this problem in Desmos and take our findings back. So I already put it in, and because by now you've gotten very familiar with putting in values into Desmos, so I won't necessarily take up your time doing that, but we can already see when I've put all of my data in, we get $14,147.69 after 9 years. So all I'm going to do is take that information back over here and I'm going to put it in my answer. And then what I'm going to do is go back to Desmos. And so that was $14,147 and was it, let me go see, was it 60 cents when you round the decimal? 69 cents. Okay, now the next one, all I'm going to do is, like I said earlier, is replace that 1 with 4 because it's quarterly. So I'm going to come back over here, simply go in, make that a 4, make this one a 4, and I get $14,595.21. Again, I'm going to take that back over here. $14,595.21. You're going to do this again, but now with 12, and you would get $14,702.69. And the last one, I'll show you again because that one is a little different when you're putting it in the calculator, is the compounded continuously. So again, switching over to red, we're looking for our future amount when our principal is 6,000 times E. The rate would still be 0.10 times 9 years. And that's what you're going to be putting in Desmos. So here I'm going to put in the 6,000. Now remember, there's no like E key. You're just going to go over to the typewriter and put E. And then we're going to go back to the numbers, and it's going to need an exponent times the 0.1 times 9 years, and we get $14,757.62, and that will be my last value, $14,757.62. Now, if for any of this it asks you, this is asking you for the amount, like how much was in the bank account. But if it would ask you how much of that was interest, like how much of that was, let me switch colors to green. how much of that was essentially you making money for just leaving your money in the bank, it would be interest. And the way you would get that is you would take the future amount, minus the principal or the original amount, and that would get you the interest. So like on that first one, this one right here, compounded annually, so that would be the $14,147.69 minus the $6,000, and all of that would be how much interest it earned for just sitting there. So let's keep the party going for number 12. 12 is a multi-step problem. You're asked to do a few things with your functions first. This is function notation. This one's composition. This is division, dividing functions, and this, of course, is another form of composition, but going the other direction. But notice, really important, it's not asking you to find that composition or that division. It's asking you to find the domain. So you have to first do the operation or the composition and then look at the image to figure out what the domain is. I will tell you this one was a very commonly missed problem because some of you were very fixated on just doing the operation or the composition and not looking at what it's asking you. So let's do this together. I'm going to switch over to green. I'm going to do the division. So this would say g of x over f of x. G of x is 1 over the square root of x divided by x squared minus 4. So you could put it exactly like this, that's fine, or you could take it a step further and say, okay, well that's 1 divided by the square root of x divided by x squared minus 4 over 1. We know with division that makes you change it to a multiplication, and you use your reciprocal of the second function. And so you get 1 over the square root of x times x squared minus 4. So it really doesn't matter. And in fact, I'll show you both ways. So let me erase this real quick. And I'll be able to show you both ways. Going into Desmos. So take a look at this one. This is with me doing the operation, and right below it, I'm going to do what it originally was, which was 1 divided by square root of x divided by x squared minus 4. And we see we get the exact same graph. So you could just do that and look at your image in Desmos, or you could simplify it. It's really your prerogative. And so at the end of the day, the green or the red, we are looking at this image and we're figuring out the domain. So remember, domain, we read it from left to right, or small to the large. And notice there's an asymptote in there, and that's keeping it. It's that force field, that barrier. See how it's shooting down, and then it goes on the other side of 2 and shoots up. So that 2 is that force field. So it looks like it first hits on the scene when your x is 0, right there at the origin, and it goes 0 to 2, and then 2 to infinity. And that would be what you would put in your domain spot. So here, this would be 0 to 2, union 2 to infinity. Or you could put a comma. So there is your domain of g of x over f of x. Now let's talk about compositions again. And on this one, I'm going to switch over to colors. I'm going to do this function in blue. Yellow's kind of hard. I'll do black, and this one in black. So when we're looking at the second one, we're looking at g of f of x, which this means that the whole f function is going to go live in that g function. So what does that look like? That looks like 1 over the square root, but instead of seeing the x, we're going to put in x squared minus 4. And again, nothing we could really do here other than go to the graph and see what this looks like. So let's go over to Desmos. I'm going to hide these two. I'm going to activate this one that I already preloaded in there. And now all we have to do is read our domain. So again, we see a disconnect, or it appears on one side and then it appears on the other side, and we see asymptotes again. We see asymptotes at x equals -2 and x equals +2, and so that means that we need to read it from left to right. So it's -infinity to -2, but then it picks up on the other side of 2, +2, and continues on for forever. So what does that look like when we write our answer? Looks like it's -infinity to -2 union 2 to infinity. One more on this and we're going the other direction. So now in this case, we're going to be putting the g function right there into the f function. So let me see what that looks like. That would be f of g of x, or g of x is going to go into that function. We get parentheses squared -4, and what goes in here would be 1 over the square root of x. And again, you could take a minute to try to simplify, but what's the point when you're trying to get the graph and read the domain of that? And so now let's come over here. Let me hide this one and activate this one. And lo and behold, we see that it does not appear on the left-hand side of 0. The first place that we see that it comes onto the scene is it gets super close to 0 but doesn't touch, so that is 0 to +infinity, and that is our domain for that problem. 0 to infinity. So we answered the domain of our operations of functions, and compositions of functions. So I think we have enough time to do problem 13 on this particular video. And so let's take a quick peek at 13 and let's see what it's asking us to do. It says use like bases and exponents to solve this equation. Now, right off the gate, I see that our base, this would be my base and this would be my base, very similar, but they are not a liked base. So that means we're going to have to manipulate one or both to make them have what's called like bases. And right out the gate, I see, oh, 1/2, I know that I can make that into a 2 with a negative exponent, if you remember your negative exponent rules. So I can rewrite it as 2 to the -1, is that this right here is the same, that is the same as 1/2. If you don't believe me, you're welcome to go to your calculator and explore that a little bit more, but that's the power of negative exponents. And so here, I get 2 to the -1 raised to n plus 5 equals 2, 5n minus 10, and now we have like bases. So it says whenever you have a like base equal to another like base, you can set their exponents equal to each other and solve. -1n plus 5 equals 5n minus 10, and solve. -n minus 5 equals 5n minus 10. It doesn't really matter which way you move as long as you are being consistent. So I'm going to take my terms with the variables to the left-hand side and my constants to the right-hand side, so that I get -6n, this is gone, equals this is gone, equals a -5, divide both sides by a -6, and I get n equals +5, 6 as an answer. And that's all I can do on that one.